This is a production of the Chemical Education Material Study.
Living systems ingest foods, water, and surrounding atmosphere, then synthesize essential structural materials and sources of energy from these raw materials. The rates of these syntheses are controlled by well-defined molecules called enzymes. You have thousands of different enzymes in your body. If any one ceases to operate, you'll get sick. But when successful, a single molecule of an enzyme can accomplish as many as 100,000 syntheses per second. Enzymes are catalysts. We'll look into how catalysts operate.
In most chemical reactions, the reactants are consumed. A piece of sodium placed in water diminishes in size. Copper begins to disappear when placed in nitric acid. The poisonous fumes from this and other experiments are drawn away by a fan beneath the laboratory bench. When the sodium and copper are consumed, the reactions stop. Adding manganese dioxide to hydrogen peroxide produces another rapid reaction. But unlike copper or sodium, the manganese dioxide does not diminish in size. At least we cannot see any change. But let us check more closely to see if the solid is consumed in the reaction.
We allow the manganese dioxide to dry, then establish its exact mass before repeating the reaction. Note the balance is adjusted to the mass of the sample. The solution of hydrogen peroxide by itself looks stable, but actually it is decomposing slowly. The products are water and oxygen gas. With manganese dioxide in the solution as before, the reaction rate is again rapid. Oxygen gas is evolved, as you can see, by its effect on the glowing splint. Again, we allow the manganese dioxide to dry before replacing it on the balance. The mass is unchanged, showing that the solid has not been consumed in the net reaction. Thus, the manganese dioxide does not appear in the equation for the net reaction, which reads hydrogen peroxide gives water and oxygen gas. The equation for the similar reaction without manganese dioxide is the same. The net reactions are identical. The only effect of the manganese dioxide is to give a faster reaction.
There are many substances which increase the rate of chemical reactions without being consumed. Over 100 years ago, such substances puzzled Berzelius, the great Swedish chemist. He named materials that increased reaction rates without being consumed catalysts. But Berzelius could not explain why catalysts are not consumed. To him, they had a new power, a hidden power quite different from the usual chemical reactivity. Even today, we do not know how some catalysts, such as manganese dioxide, really work. However, one well-understood example of catalysis is the decomposition of formic acid. The equation for the net reaction reads, formic acid gives water and carbon monoxide. At room temperature, decomposition occurs, but much too slowly to be seen.
But adding concentrated sulfuric acid to the formic acid leads to rapid decomposition, as shown by the generation of carbon monoxide gas. Experiment shows sulfuric acid is not consumed. It is acting as a catalyst. Other acids, such as phosphoric, also catalyze the decomposition. Each acid has its own rate. Phosphoric, a weaker acid than sulfuric, must be heated to give an appreciable rate. But how do these catalyzing acids function without being consumed? To find the answer, let's begin with pure formic acid. These molecular models represent liquid formic acid. Each model is surrounded by many others, all colliding in a random fashion. Most collisions lead to little transfer of energy, and the molecules rebound without decomposing. This is true even with the sulfuric acid catalyst present.
To study an effective collision, we use a schematic representation of sulfuric acid and formic acid molecules. The formic acid consists of 1 carbon, 2 oxygen, and 2 hydrogen atoms. Sulfuric acid, the catalyst molecule, colliding with the proper geometry and sufficient energy, donates a proton to the formic acid molecule. By losing a proton, the sulfuric acid forms a hydrogen sulfate ion. The formic acid molecule, by accepting a proton, forms an intermediate molecule which will undergo further reaction. In the intermediate, this bond between the carbon atom and the oxygen atom is weaker than in formic acid. When collisions with its neighbors impart enough energy to the intermediate, the weakened carbon-oxygen bond splits. This gives a molecule of water and a second intermediate molecule, which can react with a hydrogen sulfate ion and donate a proton. This regenerates the sulfuric acid and releases carbon monoxide. So, in the first step of this reaction, the catalyst donates a proton to the formic acid molecule and is chemically consumed. In the final step, by accepting a proton, the catalyzing acid is regenerated. It is regeneration which explains a catalyst's unique characteristic of not being used up. Why are the rates of the catalyzed and uncatalyzed reactions so different?
We know that the rate of reaction at a given temperature depends on the activation energy, which can be presented on a potential energy diagram. The curve represents the change of potential energy during a reaction between two particles. The high point of the curve shows the activation energy barrier to the reaction. We follow the progress of this typical simple reaction by watching a point on the curve. Changes in position as the particles approach each other are represented along the reaction coordinate. As the particles come closer, the potential energy increases. If the collision is sufficiently energetic, the activation energy barrier is crossed. Bonds rearrange, and the particles react. But when colliding particles do not transmit enough energy to cross the barrier, they rebound without reaction. The barrier for the uncatalyzed decomposition of formic acid is high. The energy of collision between formic acid molecules is almost never enough to reach the top of the barrier and rearrange the bonds in a single step. Virtually no decomposition occurs in pure formic acid. The rapid rate of the catalyzed reaction suggests a low activation energy. Here are the experimentally determined energy requirements for sulfuric acid catalysis. Either kilocalories or kilojoules may be used. The 3 sections of the curve show that the reaction occurs in 3 steps. The highest point on the potential energy curve determines the overall rate of reaction. Comparing the height of the barrier for the uncatalyzed reaction with that for the catalyzed reaction, we find a significant difference. The lower activation energy of a catalyzed reaction allows more reactions to occur in a given length of time.
The reaction of formic acid as catalyzed by sulfuric acid will be repeated to show the energy requirements for each step. The first barrier is encountered upon collision. If the collision has sufficient energy and the proper geometry, a proton is transferred to form the first intermediate, and the barrier may be crossed. If the intermediate receives additional energy from collisions with its neighbors, it will pass over the middle barrier, breaking the oxygen-carbon bond and forming the second intermediate. The third curve represents the transfer of a proton back to a hydrogen sulfate ion. This regenerates the catalyst.
When a catalyst is present, Does the uncatalyzed reaction continue? Yes, at its own slow rate. Only a few molecules have enough energy to follow the uncatalyzed path. The catalyst provides an additional and easier series of steps for the reaction to follow. It is the height of the highest barrier, not the number of steps, which determines the overall rate. Now let's study another reaction. Hydrogen gas from this cylinder combining with oxygen from the air to produce water. When hydrogen flows into air at ordinary temperature, the reaction is slow. Not enough water is formed to condense on this mirror. When hydrogen gas passes over the platinum gauze, the reaction between hydrogen and oxygen speeds up. Water condenses. The platinum is a catalyst. The heat of reaction ignites the hydrogen. We extinguish the flame before trying the other metals. The iron gauze has no visible catalytic effect on this reaction. Neither does the copper gauze. The catalytic platinum surface provides more favorable geometry and bonding properties than iron or copper. The platinum glows because the heat of reaction is so large. This molecular representation of hydrogen and oxygen gas shows that while the molecules do collide, they seldom react to form water. Even when the platinum catalyst is present, most collisions with it do not lead to any reaction. Now look at a catalytic reaction that does produce water. Here is an oxygen molecule approaching a platinum surface. When an oxygen molecule strikes with favorable geometry, it adheres to the surface and separates into two atoms. Hydrogen molecules can now react with the adsorbed oxygen atoms to form water molecules, and the catalytic surface is regenerated.
This potential energy diagram shows the two steps in the catalytic reaction. The first barrier is passed as the oxygen bond breaks and the atoms are adsorbed. Only about 1 in 1,000 collisions leads to adsorption. This is the slower step. The second step, in which hydrogen molecules react with the adsorbed oxygen, has a much lower barrier. Almost every collision forms a water molecule. This leads to regeneration of the platinum surface.
Catalysis finds an unusual but practical use in crime detection. This police chemist is examining a broken bottle found at a murder scene. Are these specks blood stains? If so, they contain peroxidase, an enzyme which is an effective catalyst for the reaction between acidified benzidine and hydrogen peroxide. The chemist prepares such a solution to test the nature of the stains. If the stain is blood, the peroxidase present in this speck will catalyze the reaction and produce a blue color. The absence of blue color in the solution is experimental evidence that the stain is not blood. The chemist tests another speck. The rapid color change shows that the second speck contains the catalyst peroxidase, suggesting that the speck came from blood.
This representation shows that peroxidase has a complex structure. The largest part is a protein. Attached to the protein is a flat portion called a protoporphyrin. And in the center of the flat surface is a ferric ion. A hydrogen peroxide molecule wandering through the liquid combines with the ferric ion of the peroxidase to form an intermediate molecule. Then a benzidine molecule collides with the protruding hydrogen peroxide. One of the hydrogen atoms of the benzidine transfers to the intermediate molecule, forming two new molecules. One, which accounts for the blue color, is a benzidine minus a hydrogen atom. The other is a new intermediate, which now loses a water molecule. This leaves another intermediate with an OH still attached to the ferric ion. This new intermediate reacts with another benzidine molecule to form another benzidine minus a hydrogen atom. A water molecule again detaches from the enzyme catalyst, which is now regenerated, ready to repeat the reaction. So catalysis helps the police chemist determine quickly whether the stains may be blood. The questions which puzzle Berzelius have now been partly answered. We know that catalysts work by introducing a new reaction path, usually with a low activation energy. And we know that at the start of a reaction, the catalyst is consumed. But finally, the catalyst is always regenerated.
Modern chemists are still seeking a better understanding of catalysis. There are still many processes for which catalysts have not been found. Indeed, catalysis is one of the major areas of current research. One application of catalysis that has benefited many of us is the increasing cleanup of auto exhausts. Today, most new autos have exhaust manifolds that contain catalysts. These catalysts convert the toxic combustion products carbon monoxide and nitric oxide to carbon dioxide and nitrogen. The result is less smog and better air to breathe. Progress occurs.